So this next talk will be given by Simon Kneuer, and it's about hardness of network satisfaction for relational algebras. Now I say nothing, but I know the title, with normal representations.
Okay, thanks for the introduction. This paper, Hardness of Network Satisfaction, is joint work with Bodirsky. And let me give you a short outline what I would like to tell you. So starting with some definitions that you might already know. So relational algebras, representations, and networks. And with these definitions, we are able to define a class of computational problems. They are called network satisfaction problems. And for this class of computational problems, there is a really big complexity problem behind. So it's a classification question of about this class, and I will tell you about this. And since this is a really big question, there's some natural approaches to taming this really big question, and this is done by normal representations that I also would like to define for you. And if we have this, then we are in the setting to where I can state you our results that are general hardness criterions for problems in this class of computational problems, network satisfaction problems. Okay, let's start with proper relation algebras that you probably know. We have a set D and an equivalence relation on this set. And now we consider the power set of this equivalence relation, and these relations, so the elements of this power set, are the domain of a concrete algebra here, where we have some operations like the union, complement, some constants, 0, 1 identity, the converse relation, and some multiplication thing, which is the usual relational product of binary relations. And so in this concrete power set of equivalence relation domain, everything is interpreted as you would expect it. Union is the set union, and so on. And now subalgebras of such an object are called proper relation algebras, and subalgebras, of course, mean that they are closed under the operations. And so we can view these objects, proper relation algebra, from a slightly different point. If we take this set of relations, so basically the domain of this proper relation algebra, and put this on the set D, then we have a relational structure. So some set together with relations. And this is a connection that I will come back later. So of course there's the general definition of relation algebras. I have it here. Relation algebras are algebras of the same type than the proper relation algebras from the slide before. And one important thing here that was already mentioned in previous talks is that there is some Boolean algebra inside this relation algebra. And yeah, in this talk it's suffices to always think of proper relation algebras, but we will use the notion of general relation algebras in one definition. Okay, now examples. In order to have a nice way to formulate examples of relation algebras, it's nice to have the notion of atoms, and these atoms are with respect to the Boolean algebra that is inside, so the minimal non-trivial elements, or if it's a proper relation algebra, relations with respect to the set inclusion. And one example that I can now formulate is the point algebra, where the set of atoms are some symbols like equality, less than, and greater than, and every other element is a union of these three atoms, and the empty set is a constant. So all the Boolean structure is somehow clear from how I notate this. But what's not clear is the multiplication, so the relational product, and this is given in the table here. For example, in this point algebra, you have the rule that less than times less than is less than. Okay, so this is something that we will see in the following. Another example is the Hansen algebra. Again, we formulate this with the atoms. We have equality and E relation, which stands for an edge, for example, and N, which is the non-edge, and everything else is a union of these three atoms. And so the atoms here are symmetric, and we have a multiplication that is given by this table. What does this mean? For example, we have here a rule that says edge times edge. So if you have the relation that's an edge relation, and you take the relational product with itself, then it does not contain edges again. So it only contains non-edges and equality. This is another relation algebra. And now what's this connection between relation algebras and relational structures? This is about representations, and we call a relational structure B a representation of a relation algebra A. If B is an A structure, this means the signature of this relational structure is the domain of the relation algebra A. So if we have a relation algebra, we interpret all the symbols of the domain as relations, as binary relations on the concrete set B. And furthermore, we want that the induced proper relation algebra on the subset of power set of B square is isomorphic to the relation algebra A as algebras. Examples of these are for the point algebra and representation is the rational numbers together with the order and equality and the order in the other way, of course, and all the unions of these three relations. So now it's really concrete binary relations on a concrete set. And now if you recall, in the point algebra, we had this rule that less than times less than is less than. And this corresponds now to the transitivity of the order. If you look at the relational product of an order, then it's clear that less than times less than is less than. A second example for this Hansen algebra, the representation, or one representation could be an countable infinite graph, which is that contains all the triangle-free graphs as subgraphs. So this means triangle-free with respect to the edge relation, and all these finite graphs are subgraphs of this infinite graph, and such a graph exists. And if we expand the structure by the non-edges and the equality and all unions of these relations, then we have a representation of this Hansen algebra. And again, there's of course the connection to this multiplication table from the last slide, because there was this rule that edge times edge does not contain edge. This corresponds now to the triangle freeness of this graph. Whenever you have an edge and another edge with same node at one point, then the last edge in this triangle is not an edge. So the last connecting relation is not an edge. Okay, with these things we can define networks, and a network for a relation algebra, an A network, is a finite set of nodes, together with a labeling of each pair of nodes. So we have V square, each pair of nodes, and we label this with an element from the relation algebra. So examples are here drawn, and of course I did not label all the pairs of nodes, but only the interesting for me. And yeah, between two nodes, there's some symbol from the coding relation algebra. And now the satisfiability, we can talk about satisfiability. And this is first with respect to a fixed representation. And this means that we can find an assignment from the set of nodes into the representation of a relation algebra, such that whenever we have two nodes in our network, then under this assignment, this tuple, this concrete tuple in the structure is in the relation that is denoted by this sign of the symbol from the relation algebra. Okay, yeah. And as next step, we talk about general first, the examples here. This point algebra network is not satisfiable in the representation that we have already seen in Q, because there's such a cycle of less than, and this, I already mentioned, this is not possible, of course, with an order on Q. On the other hand, the second example here is satisfiable. So of course you cannot satisfy it by mapping this to a triangle of edges. This is not possible in the Hansen graph. But this left edge here, you can also map to a non-edge, and then it's totally fine. In general, we say that an A network is satisfiable if there exists some representation C of the relation algebra A, such that this is satisfiable in the network is satisfiable in the representation C. And with this satisfiability, we can state a computational problem. This is called the network satisfaction problem for a finite relation algebra. And it's to decide whether a given A network is satisfiable. So I recall it. The question is, does there exist some representation of this relation algebra such that the given A network is satisfiable in this concrete representation? And this is a class of computational problems. So one could be interested in classifying them, or for example, pointing out which of them are polynomial time tractable. So they have different complexities, and maybe it's interesting to know which of them can be solved in polynomial time. And this was stated as a classification question by Robin Hirsch in 1996. And he called this the really big complexity problem. And he also gave an example why this is really big in 1999. For example, there exists a finite relation algebra where the network satisfaction problem is undecidable. So maybe this gives you some intuition. There very hard problems in this class, and therefore it's maybe natural to focus on subclasses of finite relation algebras that has nice properties. And these nice properties are given by the representations of the finite relation algebras. And therefore, Hirsch introduced the notion of normal representations. And this is the following. So first of all, we have the definition of atomic A networks. And these are A networks where we now are not allowed to label all nodes by arbitrary elements of the relation algebra, but only by atoms. So each two nodes get a label, and this is an atom of the relation algebra. And furthermore, we want to have this, what I would call local consistency rule here, which means whenever you have a triangle that you labeled with atoms, then this should be consistent with the multiplication rules in your relation algebra, because otherwise it's not possible that this network could be satisfiable in some representation of the relation algebra. So this means whenever you labeled something with f of AC, then this should be contained in the relational product of f of AB with f of BC. And if a structure B, a representation of a relation algebra, satisfies every atomic A network, so is very, very, very large or rich in some sense, then we call it fully universal. And we call it square if the maximal element of the relation algebra is full B square. And a structure is called homogeneous if every isomorphism of finite substructures can be extended to an automorphism. So this means whenever you see in your structure two finite pieces that are isomorphic, you can shift them by a global isomorphism of the structure, one to the other. And now if a representation satisfies these three things together, so it's fully universal, square, and homogeneous, the representation is called normal. And with these normal representations, we are in the class of computational problems where we can, where our results live somehow. And so this is about finite relation algebras that have a normal representation B. And suppose additionally that there exists an element of the relation algebra such that the binary relation in this normal representation is a non-trivial equivalence relation with finitely many classes. So non-trivial means that it's not the identity and not full B square. And okay, finitely many classes means finitely many equivalence classes, of course. Then we know that the network satisfaction problem of finite relation algebra A is NP complete. And of course, NP completeness has two parts, NP containment and NP hardness. And the containment is for finite relation algebras with normal representations somehow straightforward. This is not the key, or not what we proved here. This is an observation that one could make for all normal representations. But what we proved is that then the network satisfaction problem is NP-hard also. So how can you use this result, or what does it mean? You can apply it to classify some complexities for concrete relation algebras or network satisfaction problems. For example, relation algebra number 13, where the enumeration is due to Andreka and Maddox, with domain again given with the atoms, so equality H and N, and the multiplication in this table here. You see E times E is in this case equal or E. Then if you consider two infinite peaks, so two infinite graphs where each two nodes are connected, and you take the disjoint union of them, and now add all the non-edges, so basically everything that is between these two components, then this, and all unions, of course, of edge and non-edge and equality, then this is a normal representation of this relation algebra number 13. And E together with equality is a non-trivial equivalence relation. And it has exactly two classes, because we started by a disjoint union of basically these two classes. And therefore, we have that the network satisfaction problem of this concrete relation algebra is NP complete by our result. So let's go to the second result, which is somehow in the same spirit. It's again finite relation algebra with a normal representation, and we suppose that for all elements of the relation algebra, the concrete relation in the representation is not a non-trivial equivalence relation. So there exists no non-trivial equivalence relation. And additionally, suppose that there exists some atom A that is symmetric, so self-converse, and A times A does not contain A, some multiplication rule. Then again, the network satisfaction problem of this relation algebra is NP complete. And we also can apply this to a concrete example, the relation algebra number 17 that I have already shown to you, because it's the same or it's this Hansen algebra. I called it Hansen before. And here we have that the countable universal homogeneous triangle-free graph is a normal representation. So this is an infinite graph where all induced subgraphs do not contain triangles. And if we expand this again by all the non-edges and the equality and all unions of these three relations, then we get a normal representation of the relation algebra number 17. And one can check that, of course, in this on this structure or in this relation algebra, there is no non-trivial equivalence relation. And we also have some binary, some symmetric atom here, the edge, where it holds that E times E does not contain E. This we already have seen. This corresponds to this triangle freeness. And therefore we apply again this result and get that the network satisfaction problem of this relation algebra is NP complete. Okay, so let me finish with some open problems in this direction. There's a general conjecture about the complexity of the network satisfaction problems of relation algebras with normal representations. And this conjecture states that they are NP complete or in P. So basically there are conjectured to be no NP intermediate problems in this class of computational problems. And in order to solve this or do some steps towards a solution, one could show this conjecture, for example, for relation algebras without non-trivial equivalence relation. And then use our hardness results to get one side of this classification. Another class that could be interesting are the relation algebras where all non-trivial equivalence relations have infinitely many classes of size 2. Or the same with infinitely many infinite classes. This could be also very interesting. And yeah, the last most general thing in some sense would be the relation algebras with only symmetric atoms. This would be very interesting. And yeah, so thank you for your attention, and feel free to ask any questions.
Okay, thanks, Simon, for your talk. Are there any questions, remarks? Oh, I have at least one question or remark, or maybe for future work. The satisfiability problem asks whether the satisfiability condition can be fulfilled for all pairs x and y. Maybe it could be interesting to look at some kind of approximation of these. There's only a certain fraction of these satisfactions, these constraints has to be fulfilled. Similar as in satisfiability problems, you have to fulfill these fractions of clauses to come true. Could this be interesting for you? Is this an idea for future research? Did you thought about it already?
I did not thought about this, but yeah, so maybe for some background, we translate this question about network satisfaction problems into a question about constraint satisfaction problems. And there's a large theory. And in this theory, there's also this direction that you mentioned, like counting how many constraints are satisfied. And this is about, yeah, valued CSPs. And this is one direction that is studied, but so far not
yeah,
not with
whether your transformations are preserving this property.
Yes,
I use the results from there. Yeah. I don't know it. It's only thinking about
I guess for normal representations, this should be possible. I would guess. Yes.
Okay. Yeah. Peter?
Thank you. Have all the 3 atom relation algebras been classified according to what the complexity is of their, yes?
Yeah. So this was done before, but in the paper that's by Hirsch and Christiani, there were basically these 2 cases were left open, and now it's all small relation algebras.
And maybe related to the previous question, you mentioned the CSP, and I mean, the dichotomy conjecture was solved there, but is it likely that any of the techniques are applicable here, or is there no real, I mean, you mentioned there's some map into that area, but the connection, how tight is it?
It's really tight. So the dichotomy conjecture is solved for finite CSPs.
Yes.
And what relation algebras or these normal representations are naturally are infinite domain CSP. And this is a very, very close connection. So the network satisfaction problem for normal representations is an, yeah, maybe historically a very first CSP, I would also say. And therefore, for infinite domain CSPs, there's also a conjecture, and this is open. And this conjecture about network satisfaction problems is the rephrasing of the general conjecture in this subclass. So.
Thank you. That's interesting.
Okay, are there further questions, remarks? Okay, doesn't seem to be the case. So thanks the speaker and the commentators and the questioners for the talk and the questions again.